Hi everybody, so today's video will be about another one of the in-person optical mineralogy demonstrations that I do. This in-person demonstration essentially consists of building a little polariscope around a topaz crystal that has been cleaved so that you can look down the C crystallographic axis. Here are the materials we'll use in our demonstration today. There's a small LED light box that's going to be our light source. I find this is a bit too bright just by itself, so we've also got some regular old sheets of paper we're going to use as light diffusers. There's also 2 sheets of linear polarizer for our upper and lower polarizers, and our topaz crystal. Now, topaz has a perfect cleavage plane perpendicular to the C crystallographic axis, and we are currently looking down on that perfect cleavage plane in this view. Here's a summary of all the pieces we're going to use in our experiment today, the most expensive of which is actually the piece of topaz. Let's take a look at what happens when we build a polariscope around our topaz crystal. This is usually best done in a darkened room. Here we've got our cheap light box on in a darkened room. It's a bit too bright and the light is not quite as diffuse as I would like it, so I just add in a couple pieces of regular old paper here to act as light diffusers. Next up in our polariscope setup, we'll add on our lower linear polarizer. The topaz crystal is added on next, and I'm placing it here in a specific orientation. There are many other experiments that can be done with this setup by rotating the topaz crystal, but for today, this orientation is going to give us our best view at something called the optic axes. We now bring in our upper polarizer, which is perpendicular to our lower polarizer, and in this orientation, our topaz specimen is at extinction. It's not really letting light through. However, the inclusions in our topaz crystal are shining brightly here. Polariscopes are a great way to identify and understand inclusions in crystals. But that's not the point of our experiment today. Today we're going to look for the optic axes of our topaz. And in order to do that, we're going to change our viewing angle with respect to the topaz. When we were looking directly down on the topaz, the dark region we saw was actually part of something called an isogyre. As we change our viewing angle, you'll notice the isogyre narrows and becomes more defined, and changing our viewing angle further following along this isogyre leads us to the optic axis. So unfortunately, my camera here isn't really doing the optic axis justice in this view, and it takes a bit of effort to get the camera to actually focus properly on this feature. This is actually part of the experiment that's much better in person, is that you don't really have this problem when viewing it just with your eye. This frame in our video is pretty good, however, and you can see the optic axis. So what's going on here is you've got 2 isogyres going north and south out of the optic axis, and the optic axis itself is actually at the center of a bunch of concentric rings of color known as isochromes. We've found one of our optic axes, but our topaz is actually what is known as biaxial, meaning it has 2 optic axes. And these axes aren't randomly oriented, they're related to one another by something called the 2V angle. We're now going to rotate our view through this 2V angle until we find our other optic axis. So we've rotated past our initial starting position. Once again, you can see the isogyre becoming more and more defined. It takes a bit to work out the focus going on here as well. And we eventually end up with a view looking down our other optic axis. We'll take a moment now and rotate back and forth between our 2 optic axes, so once again you get an idea of how these are related to one another geometrically. So we are rotating through our 2V angle back to our original optic axis, and once again we can rotate back through that 2V angle and go see our second optic axis. So you may be wondering to yourself right now, why do I care about these optic axes? Well, the relationships between the optic axes and the optics of our crystal in general can be used to either identify unknown specimens or to figure out how a known specimen is oriented. Our crystals are anisotropic with regards to their physical properties, which simply put means our crystals are different in different directions through the crystal. And so being able to orient a crystal appropriately can be important for many high-tech applications. Let's return to a view of our topaz crystal in our polariscope where we started out and talk a little bit about symmetry. Our topaz crystal is orthorhombic, meaning that it has 3 crystallographic axes that are going to each be associated with an element of symmetry. These axes are all perpendicular to one another and of different lengths. Our topaz is of crystal class 2 over M, 2 over M, 2 over M. So that means each of our axes is going to be a 2-fold rotational element with perpendicular mirror plane. Here are these symmetry elements for our crystal. These are going to be our crystallographic axes for our topaz, but each of our crystallographic axes are actually going to be unique, and so we need a bit more information to figure out which direction is which in our crystal. The C crystallographic axis of our topaz is going to be perpendicular to the perfect cleavage plane, but the A and B axes are a bit harder to figure out which is which. However, using our optics data, we can figure out that the optic axes of our topaz are going to lie in the AC crystallographic plane. So when spotting the 2 optic axes looking at our topaz, we've also fully figured out then the orientation of our crystal, thanks to that helpful cleavage plane as well. The really big picture here is that our minerals are defined by their chemistry and structure, and that chemistry and structure is what gives us the symmetry we see at the macroscopic scale, as well as the optical properties. All these concepts are related. And this is pretty much the point of Snellius minerals. How can we use light to better understand our mineral specimens? If you have any questions or comments for us, feel free to reach out at snelliusminerals@gmail.com. And there are a whole bunch of mineral specimens useful for exploring optical mineralogy at the eBay store Snellius Minerals. Here are the references I used in the creation of today's video. Thanks again for watching, and have a great day!